All right, so I'm Ankur Moitra. I might as well say my last name too. Whoop. Yes. Already, okay. So I'll be talking about beyond matrix completion, and this is based on joint work with Boaz Barak. Can you guys hear me all right, or is it too loud? All right, so let me tell you at the outset what this talk is going to be about. The focus of this talk is on some of the algorithmic and statistical problems that arise out of recommendation systems. But what I'll be interested in is moving beyond the matrix setting and understanding to what extent when you work with higher order objects, namely tensors, does that lead to better recommendations but at the expense of introducing computationally difficult problems. So let me start off first with just a basic introduction to recommendation systems and thinking about them as very large, partially observed matrices. And then I'll tell you the story of matrix completion, and then I'm going to tell you the story of tensor completion and how it's very different in terms of the interaction between statistics and computation. So, the usual way to start these talks, unfortunately, is a little bit canned. So, what are you supposed to talk about when you talk about recommendation systems? You're supposed to talk about the Netflix problem, which about a decade ago, Netflix issued a challenge to try and improve upon their recommendation algorithm in terms of some quantitative measure, namely the root mean squared error of its predictions. Now, you can think about the data set that they released as being a very large, partially observed matrix in which each row represents a different user and each column represents a different movie. And when an entry is observed, all it is some numerical score from 1 to 5 stars based on how much the user liked the given movie. So pretty simple, but I thought I'd mix it up a little bit. And a lot of times you don't actually see something about the data. So in fact, for the Netflix problem, there were about 500,000 users and 18,000 movies. And one of the things that really surprised me the first time I saw it was that this matrix is actually not that sparse. So if you think about the typical user, what you're really asking is, of the 18,000 movies that they could have reviewed, how many did they actually review? And it might surprise you, as it did me, to know that the answer is well over 1%. So the typical user reviewed well over 200 movies in this database. And this is because what they released was actually hand-tuned to focus on just the users who had reviewed tons of movies and which movies had been reviewed by many people. But now onto the math and the modeling. Really, the focus in matrix completion is on a very basic problem, is given this very large, partially observed matrix, which is not as sparse as you might think, well, can you approximately fill in the missing entries? Now, if you can do that, then these missing entries that you're getting good estimates to, that gives you a baseline for each user how much they would like the different movies, and it tells you something about which movies you should recommend. Now, in order to meaningfully say that you can fill in the entries of this matrix, you're going to have to assume something structural about the matrix. And I want to spend a little bit of time thinking about what the assumptions are, because I'll want to push those to the case of tensors too when we move to higher order structure. But the usual assumption is that this underlying matrix, this matrix M, which you would get if you coerced every user to review every different movie in the collection, well, the usual assumption is that this unknown matrix that we observe some of its entries is approximately low rank. And the way to think about this is that given this matrix, you can approximately write it as the sum of not too many rank 1 outer products. But what you should really focus on is, what do these outer products mean? So one way of thinking about how this matrix would have low rank structure is to think about some sort of underlying categories. You could have some movies fit into the category of drama. So in that case, you could think about one of these rank 1 terms as being owing to that category. And the first column vector will have an index for each different user in the collection. And its intensity will represent how much a given user is interested in drama. And the same way, this row vector will have an index for each different movie. And its intensity will represent how much a movie would appeal to someone who's interested in drama. So the same way, you could have other categories like comedy, same deal with the intensities, and it would have some approximately low rank structure. And for all of the different categories. So this is one way that this underlying matrix would have enough structure that you could do something meaningful about approximating its unknown entries, is if you assume M has some approximate low rank structure. And one way that that could arise is from some latent categories that you don't actually see. So when you see how much a user likes a given movie, it's some conflation of some factors that you don't see, like what that user's interests are and what categories describe that movie. Now, the usual model for matrix completion, you also have to assume something about how the observations are given to you. Now, I have to confess that I'm going to state an assumption here, which is the usual assumption in matrix completion, is that the entries are uniformly observed. So you're given some fixed set of entries, and you observe random locations in the matrix. Now, this is a pretty unrealistic assumption, because that's not how I watch Netflix. I don't choose a random movie and then decide to review it. But the truth is that the algorithms that I'm going to describe in this talk, both in the matrix and in the tensor setting, they actually work for much more general stochastic models. It's just a pain carrying around all of that extra notational baggage about what the underlying sampling procedure is. So I'm going to stick with that assumption for now, and I can talk about it a little bit later. But now we have a model, right? We have an underlying approximately low-rank matrix, and we're given random observations from this matrix. And we have both an algorithmic and a statistical question. The statistical question is, how few observations do we need to actually recover the underlying matrix? But I want to separate that from the algorithmic problem, which is there an efficient algorithm to actually accomplish that task? One of the real differences between the two stories I'm going to tell you is that in the matrix completion setting, you get the best of both worlds, and statistics and computation are not really at odds. But as soon as you work with higher order objects, we'll quickly see that there really is a tension between the two. So that'll be my allusion to what's going on. But let me, for now, focus on the story of matrix completion, because it's a really nice story that generalizes some of your intuitions from compressed sensing. So if you're faced with this matrix completion problem, given random observations from an approximately low-rank matrix, and you want to recover the matrix, your first cut approach would be something like this. So M is going to denote the underlying matrix, and omega denotes the locations which you observe. So they're just pairs of user and movie, and then you observe the entry in M there, Mij. And one natural approach for trying to recover something that's a good approximation to M is to take your observations so far in the set omega and look for a matrix X that's totally filled in, that agrees with your observations so far, so it has average error, let's say at most eta. But among all the possible ways of completing the matrix which agree with your observations so far, you could look for the one that has the smallest rank. This is some notion of looking for the lowest complexity hypothesis that agrees with what you have so far. But the trouble is that this problem is very difficult to solve. It's non-convex. It's really hopelessly non-convex. And even worse, it really is NP-hard in the worst case. And what makes matrix completion such a nice story is that in spite of the fact that this natural formulation is non-convex and NP-hard, there's actually a convex relaxation that does almost as well. And you really do get the best of both worlds in terms of algorithms and statistics. So let me tell you about this relaxation, because it'll point to what goes wrong in the case of tensors too. And you can also see that it'll be a nice generalization of some things that are known in compressed sensing. So what I want to do right now is I want to define the norm that's going to be used in my convex relaxation. This norm is called the nuclear norm. So what you do is you're given some matrix X, which now is your estimate, your guess for how to actually complete the partially observed matrix. And what I want to do is I want to tell you how to compute the nuclear norm of X. So it's pretty simple. All you do is you write X in its singular value decomposition. So you write it as the product of U times sigma times V transpose, where U and V are orthogonal, and sigma is diagonal, and it has non-negative values along the diagonal. Now, the singular value decomposition exists for all matrices, so whatever X is, whatever your guess is, you compute this decomposition. But the important thing is that from the singular value decomposition, you can read off a lot of the properties that you care about X. So for example, if the singular values are sigma 1 through sigma m, sorted in non-increasing order, then you can immediately read off the rank of X just from the singular value decomposition, because it's just the number of non-zero singular values. So the same way that this non-convex relaxation that we were trying to solve, looking for the X that agrees with their observations so far and has the smallest possible rank, is just the constraint that I'm going to look for the X that has the fewest non-zeros along the diagonal in its singular value decomposition. But the same way that in compressed sensing, taking something like a sparsity constraint, like an L0 constraint, you can do well to replace it by L1. Well, the same intuition carries over here. So instead of looking at the number of non-zeros along the diagonal in sigma, what makes sense to do is instead look at the sum of these non-negative values, so the L1 norm of the entries along the diagonal. Now that's called the nuclear norm, and that gives us our relaxation. And the intuitions that are driving it are the same things that drive compressed sensing. So now here's our relaxation. This was first introduced in Maryam Faisal's PhD thesis. It's very similar to the non-convex problem that I gave you earlier. All you do is, given your observations, you look for the x that agrees with your observations so far. That's the constraint. And you're looking for the x that does so with the smallest possible nuclear norm. So now the nuclear norm is the complexity measure that's guiding your solution. You're looking for the minimum nuclear norm x that agrees with what you have so far. So Maryam Faisal introduced this, and then she gave a bunch of applications and showed that empirically this is a good idea. But some of the real theoretical justifications had to wait until later. So one of the really important works in this line was due to Cerebro and Schreibman, who showed statistical learning theory types of bounds for this type of convex relaxation. And later on, some of the other justifications for this were due to Recht, Faisal, and Perillo, who showed that it works for a related problem called matrix sensing. And then later, some very famous work of Candice Recht, Candice Tao, and Candice and Plan, and so on, showed that, let me give you one sample theorem. So I want to emphasize that matrix completion is a huge literature. But here's one example of an exact recovery type of result, is that if M is an n by n matrix and has rank R, and it's C incoherent. So I won't really need what incoherence is, but it's some notion of the entries of M being somewhat spread out to avoid some of the pathologies. But in that case, you can actually recover M from n times R times polylog n observations. And I want to emphasize something that's quite interesting about this, is that this result is clearly nearly optimal in terms of its sample complexity because, if you think about a rank R matrix, you can always write it with, as an n times R times an R times n matrix. So just knowing that M is, low rank, that means there are 2 times n times R parameters. And here you're getting away with a number of observations that's just a log squared factor larger than the number of parameters that define the model. And not only do you get information theoretic bounds that you really can recover the underlying matrix, but you get the best of both worlds because it comes along with an algorithm, a polynomial time algorithm for actually doing it, because you can solve this convex program in polynomial time. So this is a really nice case where we get the best of both worlds, and it's going to go wrong once we work with higher order structure. The other thing I want to mention is that there are a lot of other beautiful works on matrix completion. Some of the first work due to Keshavan, Montanari, and O, followed by others, which is really about analyzing things like alternating minimization, so ways that you can get similar guarantees to this theorem, that you can recover approximately low-rank matrices from few observations, but you don't even need to solve this convex program, and you can actually do something simple and iterative that's faster and more space efficient. So I don't have time to get into the full details of the literature on matrix completion. Instead, what I want to do is I want to try and move beyond it to higher order objects. And the first thing that I want to think about is the same way that I motivated the matrix completion setting. I want to convince you that there really is more structure to these types of recommendation problems, and we should think about not just matrices, but tensors. And that if we think about it only as matrices, we're missing some important dimension to the problem. So one way to think about it is that this example I introduced with the Netflix problem is really a case where each of your observations is defined by 2 attributes. When you see a numerical score, it's tied to some user and some movie. But what I claim is that in a lot of applications, each of your observations is really tied to more than 2 attributes. And if you forget about one of those attributes, you're missing some of the dimensionality to the problem. So let me give you another example from recommendation systems. So something like Groupon wants to recommend different activities to different users. And you could think about how much a user likes a given activity as just being flattened down to a matrix, where you just partially observe this matrix. But I claim you're missing an important dimension of the problem. So for example, does anyone else here like skiing? Anyone want to go skiing now? No? All right. Well, because we're missing something like time, right? So for something like Groupon, which activities you want to recommend to different users also very much depends on the season, the time of day, whether it's a weekday or a weekend. And the same way, this extra dimension is going to help us think about this underlying partially observed object as not being a low-rank matrix, but a low-rank tensor. So let me explain what I mean by this assumption. So if you take something like snow sports, you can again think about this as some sort of latent category, which now the thing that's going to contribute to this latent category is some rank 1 tensor instead of a rank 1 matrix. And all this is going to be is it's going to be a tensor product of 3 different vectors. The first one, again, represents a vector which each index represents a different user. So here the intensity represents how much a user likes snow sports. Then the next vector has an index for each different activity, and its intensity represents how much each activity appeals to someone who's interested in snow sports. But we also have this other dimension, time, which is this remaining vector, which has an index for each different time period and represents how much you'd want to make a recommendation about snow sports in the given time period. So the same way we can actually think about other sorts of recommendation systems that are fancier that actually what you're given partial access to is from a low-rank tensor instead of a low-rank matrix. So in particular, a rank 1 tensor, all you're going to get when you take the outer product of A, B, and C is the entry in some index is just the product of the entries of A, B, and C. And now we're faced with another basic question. So just like in the case of matrix completion, we had an approximately low-rank matrix, and we asked how few observations do we need to fill it in. We can do the same thing with higher order structure now too. If we're given observations from a low-rank or approximately low-rank tensor, how well can we fill it in? So that's the basic question that I want to focus on in this talk. But what will be really interesting is the nuances that come up in this story about how statistics and computation are actually at odds here, even though they weren't in the matrix setting. All right, and this is really just one piece of a larger puzzle of, when you introduce more structure to trying to solve inverse problems, it can lead to better recommendations, but it leads to inference over more complex objects. So let's try and do the easiest thing, because it's early in the morning, so why should we do too much work? So there's a very natural approach that you can try that actually has been suggested by many, many authors, which is you could try and define a notion of a nuclear norm for a tensor. So the same way that what ended up working in the matrix case was looking for the matrix that agrees with your observations so far and has minimum nuclear norm, well, it turns out you can define a natural generalization of the nuclear norm to tensors. And I won't define it, but it's easy enough to define. And you could try and solve this convex optimization problem. Look for the x, which is now a tensor, which agrees with the observations so far, and among all such x's has the minimum possible tensor nuclear norm. Now there's a trouble here, which is even though this optimization problem is convex, well, computing the tensor nuclear norm is actually NP hard. And there's an interesting story behind this. It turns out to be connected to things like quantum information theory, and it's related to detecting whether or not a given state is separable. So I won't go into details about that, but later in the talk, I'm actually going to give you some very different kind of evidence that not only is the tensor nuclear norm hard to compute, but in fact, even what it's trying to do is just fundamentally the wrong thing for these types of problems, and there are more serious barriers. Is there a question? Nope. All right, and just to take a slight detour, what happens when you take the usual matrix linear algebra toolkit and you try and apply it to the tensor setting? What I claim is you're going to have a bad time. So if you take the usual linear algebra toolkit, when you try and transport those definitions to tensors, you encounter all sorts of issues. Namely, a lot of the definitions are ill-posed, and even when they're not ill-posed, they're still computationally hard. And I think the best way I know to make this point is that there's by now a pretty famous paper by Hiller and Lim, which says it all in the title. Most tensor problems are NP hard. And if you don't believe them based on their title, here's a rather extensive list of just what they proved in this paper. Everything on the left-hand side is something that you can compute and is well posed for matrices. And on the right-hand side, it's how it goes wrong. It's either NP hard or worse. All right, so let's return to our problem. What I claim is, when we're trying to infer a low-rank tensor from few observations, there's still something trivial we can do. What I want to do now is I want to tell you the trivial algorithm. And my main goal in this talk will be to beat the trivial algorithm and to show you that you can't beat it all the way down to the information theoretic bound. So we have this approximately low-rank tensor. What I claim is there's still something we can do without doing much work, which is we can ignore some of the structure in the tensor, and we can treat it like a matrix. We can flatten the tensor, treat it like a matrix, and complete it without knowing that extra structure. So another way to put this is if we're given this low-rank tensor, n1 by n2 by n3, one trivial thing that we can do is we can just rearrange the entries of this tensor into a matrix. So we can rearrange it into a matrix where there are n1 rows and there are n2 times n3 columns. Or to put it more concretely in the example we talked about, what you would be doing in the Groupon system is each row would represent a different user, and each column would represent a pair of activity and time. And so what's important here is that we've already forgotten a lot of the important structure, because each of these columns is completely independent. So it's like making predictions about what to do, ignoring the fact that two different columns share the same activity or share the same time period. We treat them as completely different objects and we try and do inference on it, but it's still a smart thing to do. So what we're really doing is we're taking the entry in tijk and we're putting it in row I and column jk. And the important thing about this is that flattening is just a rearrangement of the entries of the tensor, so it's something we can easily do, and it doesn't increase the rank. And there's a very simple way to see that, is just to think about the rank 1 case. To notice that flattening is a linear operation and think about what it does to a rank 1 tensor. So if we had A, tensor B, tensor C, what would this flattening operation do? Well, we'd get a rank 1 matrix, because we'd get the outer product of A, which is a length n1 vector, with another vector which is length n2 times n3. And we get that vector just from taking B times C transpose, which is an n2 by n3 matrix, and flattening it to a much longer vector. So in this way, that is exactly what we get when we flatten a rank 1 tensor. We get a rank 1 matrix. And the same way that when we flatten a rank R tensor, we get something which is at most rank R for the matrix. Now, there's a big trouble with this naive algorithm, and that's my real focus, is trying to beat this naive algorithm, is if you think about it, let's make things simple. Let's set n1 equals n2 equals n3 as n, just for simplicity. Well, you're flattening this n by n by n object down to an n squared by n object. So the number of parameters that defines that rank R matrix is n squared times R. So if we use off-the-shelf matrix completion and forget about the tensor structure, we're stuck with n squared times R observations. And also, kind of shockingly, there's a big literature on tensor completion, which, in spite of the fact that the tensor nuclear norm is hard to compute, they suggest all sorts of other fancy norms. But the shocking thing is that none of those other norms give better guarantees than this naive flattening. They all only are able to complete tensors by forgetting all of their structure and getting down to something n squared times R. And my main goal in this talk is to understand this question: can we beat flattening? And I'm going to tell you that the answer is yes. And the way that you should think about this mapped back to the recommendation systems is you actually can make better recommendations than just treating each column, which is an activity cross-product time pair, independently. You can actually leverage some of the structure, and we'll be able to get down to n to the 3/2 times R, and we're going to show a matching lower bound that under some standard complexity assumptions, you actually can't get to the information theoretical limits for this problem. All right, so what I want to do now is I want to tell you about the guarantees of this, but the way that I'm going to work up to this is I'm actually just going to tell you a corollary of the main theorem, and I'm going to tell you the main theorem at the end. So let me tell you what I think is a very interesting corollary of what I'm going to prove. So let's consider the following simplified model. So we're given some approximately low-rank tensor, so it's written this way. Now I'm going to make things a little bit simpler, and I'm going to avoid some of the pathologies of the way that the entries can line up and cancel each other out. And I'm just going to put in a little random variable as a coefficient in front of these rank 1 terms. This is just the corollary of the main theorem, so this is just to illustrate what the types of bounds imply. You can take it to be a standard Gaussian random variable or what have you. Now the way to think about this is that if A is a unit vector, then its typical entry, if it were random, would be about 1 over root n. So the typical entry in a rank 1 tensor is 1 over n to the 3/2. So the typical variance of the entry in some low-rank tensor is about 1 over n cubed. And you're adding up R of these things. So just under the condition that the entries in the tensor are somewhat spread out, so that the typical entry has about the right variance, it turns out that with only n to the 3/2 times R observations, you can actually learn almost all of the entries almost entirely. So in polynomial time, for a 1 minus little o of 1 fraction of the entries, you get an estimate x, which xijk is 1 plus or minus little o of 1 times tijk. So almost all the entries you know almost entirely. And this even works with some modicum of noise. And this type of variance bound, what you're really assuming is that the entries in these AI, BI, CI vectors are at least somewhat spread out. It holds for things like if you were to construct the factors randomly, or even when the factors have really large inner product with each other, you can still find plenty of scenarios where this type of condition holds. And one of the really funny corollaries about this, which I want to emphasize is kind of unique about this, is you might want to think about this theorem in the small rank case, where R is polylogarithmic or something else, because those are the natural types of objects you'd be working with in recommendation systems. But something funny happens when you plug in larger values of R. So if you plug in R is n to the 3 halves minus delta. So it's a huge rank tensor. Its rank is well beyond n, and that's called the overcomplete case. Then this theorem is still interesting. It tells you you can observe a little o of 1 fraction of the entries of the tensor and still be able to complete almost all of its entries, even when you're highly overcomplete. And one of the really funny things about this is if I gave you the whole tensor, and there was no observation model, and it was overcomplete, we don't even have algorithms for decomposing tensors like this. So this is actually a result which is fundamentally about convex programs, because the only thing we know how to do here is actually to predict the entries, but we don't actually know how to find the decomposition. And things like altering minimization would not only predict the entries, but they would find the decomposition too. So that's a kind of funny quirk of this result. And the other thing that I want to tell you before moving on to a little bit of the meat is some kind of surprising connections to computational complexity. So, I want to make good on a debt that I said earlier. So I said that the tensor nuclear norm is NP hard, but I said actually it's a bit worse. So there's a sense in which not only is a tensor nuclear norm hard to compute, but even what it's trying to accomplish is just the wrong thing. So it turns out that there's a formal connection between doing tensor prediction and refuting random CSPs. So given random constraint satisfaction problems, being able to prove good upper bounds on the fraction of clauses that you can satisfy. Well, it turns out that tensor prediction, appropriately defined, with M observations, if you have a good algorithm for doing that, you can actually get an algorithm for refuting random 3-sat clauses, with random 3-sat formulas with just M clauses. So the interesting thing is that, on the one hand, if you look at this just from the matrix completion literature, you might be an optimist and you might hope, hey, I hope I can once again get a polynomial time algorithm, which the number of observations is close to the number of parameters that define the model, but then you'd be in direct competition with this competing thing from random CSPs that not only do we not have algorithms for refuting random CSPs with too few clauses, but we even know that very powerful families of semi-definite programming hierarchies fail spectacularly. So I'm not going to define what these STP hierarchies are, but this type of implication tells you almost immediately that any algorithm for solving tensor completion, you create even these powerful hierarchies of relaxations, this tensor nuclear norm, they fail even if you allow them to run in exponential time once you go just a little bit below our bound, down to n to the 3 halves minus delta observations. All right, so let me tell you a little bit about some of the meat, but that was the main background. So the main thing that I want to get across is actually, thinking about tensors is a little bit too involved for 9 in the morning. So let me make this simpler. Let's forget about tensors, and what I want to do is I want to do something pedagogical, and just think about the matrix completion case again, but tell you, in fact, how two different communities were using very similar techniques, and were doing roughly the same thing. One of those communities being matrix completion, the other one being random CSPs. And I want to tell you how they both solve the same distinguishing problem. So let's make our lives much simpler. Let's just consider, instead of even completing a matrix, let's think about trying to distinguish between two cases that we definitely should be able to. So can we distinguish between two settings, one where our matrix is approximately low rank, and the other where it has no underlying structure? So in case 1, for example, let's say that we're given access to a rank 1 matrix, except it has some noise. So it's A times A transpose plus some noise. Or more precisely, this A vector that I'm going to consider, it only has plus minus 1 entries in it. And now every entry you observe is going to come from the following distribution, For each entry you observe, with probability 3/4, it'll come from the rank 1 piece. So it'll come from AI times AJ. Otherwise, with a quarter probability, it's going to be a random plus minus 1. And it's going to have no structure to it. So that's the case where there really is some approximate low-rank structure. And case 2 is the case where there's no structure. So every entry you observe is just a random coin flip, plus minus 1. And there is no low-rank structure. And what I claim is that algorithms for matrix completion have to be able to distinguish between these two cases. Because if you think about it, case 1 is a case where the entries are somewhat predictable. Because 3/4 of the entries come from this rank 1 piece, so that means that you can at least predict those things, right? Whereas in case 2, they're completely unpredictable. So good algorithms for matrix completion will actually be able to tell you which of these two cases you're in. But the way that I've set this up, it's also not only a matrix completion problem, but also a random CSP. So on the one hand, this type of distinguishing problem has been solved by the community working on matrix completion, but it's also been solved by people working on random CSPs. Because if you think about it, the entries in this partially observed matrix, you can think about them as parity constraints on the product of entries you're looking for. So the same way, case 1 was one where I planted a good assignment because the rank 1 piece is what gives me a good assignment to a random CSP, and case 2 was the one where there is no good assignment. So in fact, the community on refuting random CSPs has also worked on this problem, and ultimately, just to give you a sketch of this connection, we end up showing is that when you ask for a matrix prediction problem, where you're trying to meaningfully predict the entries of a low-rank matrix with just m observations, there's a technical sense in which algorithms for doing that task actually give you algorithms for refuting random CSPs. That given a random CSP, this algorithm then can prove to you that it's a pretty random instance and that there is no good satisfying assignment that beats random guessing. Now, the really interesting thing is once you set up this bridge, you can start using it actually not only in the direction it's designed, but even driving in reverse. So once you have this set up, there's nothing special about matrices and 2 observations. You can instead work with higher order objects too. So once you set up this connection, algorithms for tensor prediction, for third order things now, they actually yield algorithms for refuting random third order CSPs with 3 variables per clause. And then the important thing is that we know that there are lots of reasons why refuting random third order CSPs should be hard with fewer than n to the 3/2 clauses. That immediately yields lower bounds for tensor prediction. But the funny thing is, if we had an algorithm for tensor prediction which worked with just n to the 3/2 clauses, using this bridge, it would imply algorithms for refuting random CSPs with just n to the 3/2 clauses. The bridge only goes one direction, but if you think about that implication, there actually are algorithms for refuting random CSPs with that few number of clauses. The first one is due to Koya, Oglin, Gert, and Lanka. And once you know that that result is there, you can actually try and use this result and traverse the bridge in the other direction. So it turns out that you can embed their argument into a hierarchy of SDPs and show that the SDP can also refute random CSPs. And what that gives you is it actually, through the language of Rademacher complexity and statistical learning theory, that gives you a norm with good generalization bounds. So that's the quick sketch, is that what we do is we take an algorithm for strong refutation, we embed it into the 6th level of the sum of squares hierarchy, and we end up getting a good surrogate to the tensor nuclear norm that works with just n to the 3/2 observations and beats all of the other relaxations that were proposed and is nearly optimal. So I'll quickly state what the main theorem is. This is why I didn't want to state this messy, ugly thing, but this is the thing that had the corollary in the beginning. So the main result is that if you're given observations from a noisy tensor, then actually there is an efficient algorithm that recovers some x, which the average error is actually bounded by this quantity on the right-hand side. So as m increases, you get better and better predictions. And as I mentioned, this actually has to do with refuting random CSPs. But actually, I want to take a step back and actually think about some of the broader issues. Yep?
Just going back to the last slide. So the dependence on r is going to be r squared?
No. So if you think about the typical entry in a tensor, if I created a random rank r tensor, then the typical entry would actually be root r times 1 over n to the 3/2. So the important thing about this bound is when it becomes smaller than that, because then it means that your prediction error is smaller than the typical entry in the tensor. But great question. Yep?
For instance, the
Yes, exactly. So one of the weaknesses of this is that it doesn't degenerate to exact completion in the case where there's no noise.
But also, wouldn't you expect it to can do R times n complete half times polynomial?
I don't know. I expect it, but this is just the first cut. That's a great question. Especially doing something like exact completion will be pretty interesting, and that has very different types of analysis techniques instead of through Rademacher complexity. All right, so I want to take a step back, and so what did I tell you about? So what I gave you was an algorithm for third-order tensor prediction. So when you're given noisy access to this approximately low-ranked tensor, which takes only n to the 3 halves times r times polylog n observations. Now the important thing is that if you actually could solve this tensor nuclear norm problem, this tensor prediction problem that I set up is something which you could do spectacularly well. You could do it with roughly n times r times log n observations. That's a really easy calculation. And that is roughly the information theoretic bound because you have n times r parameters that define the model. So it's a case where this is the information theoretic limit of what you can do for tensor prediction. And this is the algorithm we're giving is an a root n factor worse. But in fact, there are lower bounds for even powerful families of hierarchies that show that some of the approaches suggested don't work beyond n to the 3 halves. So it's a case where there really is a gap, at least conjectured based on these sum of squares relaxations, between the tension between sample complexity and computational complexity. And one of the things that I think is really interesting to study, more broadly, is that if you look at, some of the linear inverse literature, there's not just matrix completion, but all sorts of other problems out there. And one of the really nice takeaways is that I think convex programs are oftentimes unreasonably effective at solving problems. The first time you see how good these convex programs are that people cook up, that actually solve these, I'm given random observations from some structured object, it's amazing. But, the same point, what we did was we gave a linear inverse problem that actually exhibits a gap. So some of the other problems which we don't have good algorithms for, those are actually very natural candidates to try and understand why we're stuck. And maybe it's because you can't do everything you would think if you're an optimist. But the other point, going further, is that I think this issue of trying to understand the tension between computation and statistics is a great thing going forward. But when you think about these problems, to what extent is sample complexity and computational complexity at odds, there's a scientific question here which is challenging, is that how would you ever prove lower bounds on computation? We don't have any approach for proving lower bounds for, other than reductions. And one natural way is to actually work within frameworks of semi-definite programs so that you can actually prove at least those hierarchies that capture a lot of what we know how to do in polynomial time don't work. So one of the new directions here is that you can actually try and explore computational and statistical trade-offs without reductions through hierarchies of SDPs that capture interesting families of algorithms. So I'll stop there. Thanks for your attention, and any questions you guys have, I'm happy to take them.
So that was excellent. We've already had 2 questions, which might be the total third.
I actually have another question, which is also related to not just the tensor, but the matrix case.
Mm-hmm.
So, correct me if I'm saying something that's garbage, but I see it as you're assuming that me as a user, I'm a linear function of a few variables,
Mm-hmm.
a few hidden variables. But I might not be a linear function, but some kernelized something or other.
Yep.
Do any of these works handle such cases?
Not to my knowledge, so that's a great question. One way to think about it is you can think about the matrix case as being the world's simplest graphical model too, where you have some latent variable representing the categories of the different users, but it's a very simple kind of function that describes your observations. So you have 2 variables on top given by the user and the movie, which are described based on what their distribution is over the different categories. But as soon as you work with more interesting functions like logistic regression, then very simple types of graphical models, we don't have interesting provable guarantees, even for something like disease networks and noisy ORs, which are just logistic functions instead of linear ones, then I'm not sure I know interesting guarantees there. Yep.
So, in the case of matrix completion, there are quite a few papers about what we call 1D.
Yeah, exactly. I should have mentioned that one. So it's a censoring of linear observations, though, because. But you observe functions of you know, the matrix entries, which,
I guess I'm just seeing like I as the user, so there's some hidden variables I don't know, like what's the drama factor, the movie, the comedy factor, etc. And like I as a user, like maybe if I'm a linear function, let's say I like both drama and comedy, right? Then the more drama and comedy in the movie, the more I like it. But maybe I actually hate movies that have both drama and comedy, but I like movies that only have drama and only have comedy, right? So like I'm very nonlinear.
yep. That was great. I outsourced one of the questions to.
You can create a feature space that tries to make me into a linear thing in that feature space. I mean, is that
I'm glad Andreas is here, so this is.
Other question. Can I ask a naive question?
Of course.
So all of these methods that you describe assume that the structure you're trying to recover is low rank.
Mm-hmm.
How do you know if it is? I mean, is there any way of knowing a priori? I mean, maybe that assumption is wrong.
Well, one of the things that you can do is when you have, you know, even take the matrix case, right? So, you know, if you got something, you know, in the statistical learning theory model, you're looking for the lowest nuclear norm solution that agrees with your observations so far. If the convex program doesn't have a good solution, it has something really high in terms of nuclear norm, then that's one indication that it might not be the right thing.
Yeah, but that's sort of a, I mean, right, sure. So if it's terrible,
Then you know that at least
but
your
you
prediction.
But you don't know that there. I mean, even if the real underlying model, I mean, maybe you say comedy, drama. Maybe there are lots of categories of movies. I don't know.
Yep.
Right. I mean, it's possible. Right.
Yep.
And so I mean, but I mean, it's possible that that's the case. But still, there's a good low rank. Maybe this isn't actually a good question. There still could be a good low rank approximation, even if the real underlying model. But then you would say it's effectively low rank. So I see. So you're just being pragmatic. You say, well, if the low rank thing fits, then I win.
Sure, because you'll have good generalization bounds. There are other answers to that type of question, but that's one.
But still, you don't, when you report the low rank object, you don't report the error. Right? That is, it's not like there's, or maybe you do. Right? There's, anyway, okay. I know. I tried.